June 3, 1998. A high-speed ice train is cruising at 200 kilometers per hour through the German countryside.
Everything looks perfect on paper. The flagship of German engineering, carrying nearly 300 souls toward Hamburg.
Then, a single metallic bang changes history. A 2-inch crack in a steel tire on the third axle of the first car suddenly snaps.
It starts as a technical failure, but ends as a financial and logistical nightmare. This single fracture is about to cost 101 lives.
The broken steel rim peels away like a razor, punching through the floorboards of the passenger cabin.
The crew has no idea. The passengers see a metal bolt erupt through the floor, but the warning system stays silent.
Physics is about to take over. That loose rim is now a hook, waiting for a track switch to rip the entire train apart.
It's a cascading failure of intelligence and maintenance. $6 million of machinery turning into a pile of scrap in seconds.
You're sitting in the dining car, feeling a slight vibration. You have no clue that the bridge ahead is about to become a tomb.
High-speed rail is built on trust and precision. Today, we look at the moment that trust shattered into thousands of pieces.
This was the Eschede disaster, a moment where the best engineering in the world met its match in a tiny piece of metal.
The financial fallout would eventually reach the hundreds of millions, but the human cost is what stays with us.
The Ice One was supposed to be the future. Sleek, fast, and supposedly indestructible.
But corporate cost-cutting and a lack of oversight created a monster. They ignored the early warning signs to keep the schedules moving.
Imagine a wheel tire designed for durability being replaced by a multi-layered rim to save on noise.
Noise reduction over structural integrity. That was the first fatal decision made in a boardroom long before the crash.
They used a dual-design wheel with a rubber core. It was quieter for the passengers, but it created hidden stress points.
Those stress points were invisible to the naked eye. The inspectors were looking for cracks, but they were looking in the wrong places.
Every time that train sped up, the metal flexed. Centrifugal force was fighting the structural limits of that 2-inch rim.
Fatigue isn't just a human condition. In engineering, metal fatigue is a silent killer that waits for the perfect moment to strike.
That moment arrived at exactly 10:59 in the morning. The train was approaching a series of points near the Eschede bridge.
The logistics of the disaster are horrifying. A single mechanical snap leads to a massive structural collapse of a 300-ton bridge.
When that tire snapped, it didn't just fall off. It became a jagged spear aimed directly at the heart of the track system.
No one in the control room saw it coming. The data was clear, but the humans behind the screens failed to react to the vibration reports.
Physics doesn't wait for permission. The train hit the first switch, and the metal tire forced the wheels to jump the tracks.
It was a domino effect of catastrophic proportions. The first car derailed, then the second, and then the chaos became unstoppable.
The kinetic energy involved here is staggering. 200 kilometers per hour of mass moving with nowhere to go but into a concrete pillar.
This wasn't just a crash. It was a total structural failure of the entire transportation ecosystem.
We need to break down exactly how that crack formed. We need to look at the microscopic level to understand the macroscopic tragedy.
And we need to look at the budget meetings where they decided to skip the ultrasound tests.
The engineering was flawed from the start. They didn't account for the resonance frequency of a train moving at that speed.
They accounted for comfort, not for the brutal reality of high-speed friction.
Now, let's open the investigation files. This is how a 2-inch crack brought a nation's pride to its knees.
This is the anatomy of a disaster that could have been avoided with a single, honest inspection.
Pay attention to the details. In high-speed engineering, there is no such thing as a small mistake.
Especially when that mistake is buried deep inside a steel wheel, spinning at thousands of revolutions per hour.
We are looking at the fatal intersection of physics and negligence.
Let's follow the metal and the money.
This is the kinetic fall analysis of the Eschede disaster.
Brace yourselves for the technical truth.
The bridge is coming up, the switch is set, the tire is broken.
And there is no one left to stop the inevitable.
Let's dive into the mechanism. Let's look at the mechanical heart of this failure, which was the transition from solid steel wheels to the resilient dual design. Originally, the ice trains used monoblock wheels, but they caused massive vibrations at high speeds, making the ride uncomfortable for first-class passengers. To fix this, engineers implemented a tire and rim design, placing a rubber ring between the steel tire and the wheel body to absorb the shock and dampen the noise.
That decision was a classic case of prioritizing user experience over long-term structural safety to keep the German engineering brand looking premium. The management at Deutsche Bahn saw the vibration complaints as a threat to their market share against airlines, so they pushed for the quieter wheel without conducting long-term stress tests at sustained high speeds. They chose a design that was common on slow-moving trams but had never been pushed to 200 kilometers per hour for thousands of miles.
That decision was a classic case of prioritizing user experience over long-term structural safety to keep the German engineering brand looking premium. The management at Deutsche Bahn saw the vibration complaints as a threat to their market share against airlines, so they pushed for the quieter wheel without conducting long-term stress tests. At sustained high speeds, they chose a design that was common on slow-moving trams but had never been pushed to 200 kilometers per hour for thousands of miles.
From a logistics and maintenance perspective, the failure was even more damning because they were using outdated inspection methods for a futuristic train. The technicians were told to check for cracks using flashlights and mirrors, a method completely inadequate for detecting deep internal fatigue in composite wheels. They actually had automated ultrasonic testing equipment available, but the company didn't want the downtime or the expense of taking the trains out of the rotation long enough to do the job right.
On the morning of the crash, that fatigue reached its breaking point as the train approached the Eschede switch. The tire finally snapped, uncurling under the massive centrifugal force and slicing through the floor of the third axle like a giant rotating saw blade. It didn't derail the train immediately, but it became a literal hook that was dragging beneath the car, waiting for a piece of track infrastructure to snag on.
This is where the human error and lack of intelligence protocols come into play with devastating consequences. A passenger actually saw the metal piece erupting through the floor in car 3 and went to find the conductor. But the conductor refused to pull the emergency brake until he could inspect the damage personally. If they had followed a safety-first protocol and stopped immediately, the train would have come to a halt miles before it ever reached the fatal switch at Eschede.
Instead, the train hit the first set of points at full speed, and that dragging steel tire hooked into the rail guide, pulling it upward and forcing the wheels onto the wrong track. This caused the back of the third car to swing out wildly, smashing into the support pillars of a 300-ton concrete bridge that spanned the tracks. The bridge didn't just crack, it collapsed instantly, dropping thousands of tons of concrete directly onto the fifth car, which was moving too fast to even register what was happening.
The financial cost of this negligence started to spiral the moment the bridge hit the tracks. Not only was the rolling stock worth millions destroyed, but the entire high-speed rail network in Germany had to be shut down for weeks, costing the economy billions in lost productivity and logistics delays. The lawsuits that followed revealed that several engineers had expressed concerns about the wheel design years earlier. But those reports were buried by middle management to avoid the cost of a fleet-wide recall.
When the bridge collapsed, it acted like a literal wall, causing the remaining cars to fold into each other like an accordion in a space no longer than a single carriage. The kinetic energy was so intense that the cars were compressed to a fraction of their original size, leaving no survival space for those inside. It was a total mechanical annihilation, caused by a component that cost less than a few $100s to manufacture but a fortune in lives to ignore.
Behind the scenes, the investigation found that the tires were allowed to be worn down far beyond the safety limits recommended by the manufacturers to save on replacement costs. They were trying to squeeze every last cent out of the hardware, treating safety margins as suggestions rather than hard limits, It was a dark business lesson. When you cut corners on maintenance in a high-speed system, you aren't saving money. You're just borrowing it from a future tragedy at a lethal interest rate.
Even the emergency response was hampered by the sheer scale of the engineering failure. The bridge collapse had severed communication lines, and the wreckage was so densely packed that heavy cutting equipment couldn't even reach the victims trapped in the setter. We have to understand that in a high-risk environment, a single technical flaw doesn't just stay in the machine. It creates a chain reaction that breaks the entire survival. Infrastructure.
We see this pattern in every dark business case we analyze. The normalization of deviance. They saw small cracks in other wheels during previous months and just assumed they could hold out a little longer. They turned a blind eye to the data because the follow-the-money trail led toward high profits and on-time performance, and they didn't want to disrupt the flow of cash for the sake of theoretical risk.
But physics isn't theoretical. It's absolute. That 2-inch crack was the physical manifestation of every bad decision made in the boardroom. It was the exact point where the mechanical limits of the steel met the moral limits of the company, and the steel lost. Now, we have to look at how this disaster changed the way we build and maintain everything in the modern world.
The aftermath wasn't just about cleaning up the tracks. It was about a total overhaul of safety laws and corporate liability. The verdict on the Eschede disaster would eventually change the way the world views high-speed transport, moving from a focus on speed to a focus on total fail-safe engineering. But for the 101 victims, that lesson came far too late.
The dust hadn't even settled over the wreckage at Eschede before the forensic engineering teams began the grim task of peeling back the layers of steel. What they found was a chilling reminder of how the smallest oversight can lead to total system collapse. The investigation proved that the 2-inch crack had been growing for months, and the resilient wheel design acted as a cloaking device for the disaster. Because the rubber core dampened the sound, the usual death rattle of a failing wheel was never heard by the crew, leading to a false sense of security that ended in absolute carnage.
While the engineers were sifting through the debris, the legal and financial battle was just beginning to ignite in the courtrooms. Deutsche Bahn faced a crisis of confidence that nearly bankrupted their reputation, as the public realized that profit margins had been prioritized over human lives. The dark business element here was the systemic suppression of internal warnings. Engineers had flagged the dual-wheel design as a risk for high-speed use as early as 1992, yet those reports were archived and ignored to keep the ICE project on its aggressive expansion schedule.
The technical verdict was swift and brutal. The tire and rim design was banned from high-speed rail immediately and replaced with solid, monoblock steel wheels. We learned that in high-risk engineering, you cannot trade structural simplicity for passenger comfort without paying a price in safety. Today, every high-speed wheel in the world undergoes rigorous ultrasonic testing and is fitted with sensors that can detect microscopic vibrations long before a crack becomes a fracture. We moved from a reactive maintenance culture to a proactive, data-driven one, where the machine tells us when it's tired.
Beyond the tracks, this disaster forced a global shift in how we handle corporate accountability in the face of technical failure. The follow-the-money trail led to a massive settlement, but more importantly, it led to new European safety directives that stripped companies of the right to self-regulate their maintenance intervals. The cost of the Eschede crash reached well over $500 million in damages and reconstruction, proving once again that doing it right the first time is always cheaper than paying for a catastrophe.
For those of you in high-risk environments today, the lesson is clear. Never ignore a vibration. Whether you're operating heavy machinery, managing a power grid, or just sitting in a train car, the normal sounds of a system are your baseline. Anything else is a warning from the laws of physics. If that conductor had listened to the passenger and pulled the brake, the history of German rail would look very different. In our world, hesitation is the difference between a close call and a national tragedy.
This wasn't just a German failure, it was a global wake-up call for the logistics of speed. We now understand that as we push our technology faster and further, the margin for human error shrinks to zero. The strategic takeaway is that transparency must be part of the engineering process. You cannot have a safe system if the people at the bottom are afraid to tell the people at the top that something is broken. Survival in the modern age requires a constant state of high intelligence monitoring and the courage to stop the clock when the data looks wrong.
We've seen the autopsy of the ICE-884, and it's a blueprint for what happens when we lose respect for the forces we're trying to control. The kinetic energy of a high-speed train is a beast that must be caged by perfect maintenance and uncompromising design. Every time you step onto a platform now, know that the safety you enjoy was bought with the lessons learned at the Eschede Bridge. Keep your eyes on the details and your ears open for the shifts in the machine.
The financial and emotional scars of 1998 have finally faded into history, but the protocols they birthed remain our primary defense against the next impossible failure. We analyze these disasters not to dwell on the past, but to sharpen our instincts for the future. The 2-inch crack taught us that in the world of high-stakes engineering, there is no such thing as good enough. You either have a perfect system or you have a ticking clock.
That's our breakdown for today. Stay sharp, watch the tolerances, and never trust a machine that hasn't been tested to its limits.
And remember, the most expensive way to learn a lesson is through a tragedy. Always follow the data before you follow the profit.
Check your gear.
Stay safe.